I am Catherine Knowlton, a professor in the Department of Dairy Science at Virginia Tech, and I'd like to tell you about the research conducted in our lab. I grew up on a dairy farm, and I still own cows, so I'm very familiar with the challenges farmers face managing their farms while being true to their ethic of environmental stewardship. My research focuses on developing effective strategies to reduce any negative environmental impact of modern agriculture. That's a fancy way of saying that we measure stuff in cow manure, and if that stuff might cause problems, we find ways to get it out of there. We actually pride ourselves on finding practical environmental solutions for dairy farmers before they need them. In this presentation, we'll talk about our recent work conducting genetic analysis of manure, of all things. Actually, it's the bacteria in manure we're interested in, and whether they are resistant to antibiotics. We do cutting-edge genomic analysis on their DNA to find ways to be sure that we in the dairy industry aren't contributing to the global problem of antibiotic resistance. We believe strongly that the therapeutic use of antibiotics for animal agriculture is necessary, that it's not humane to withhold effective medicine if a cow is sick. But we also believe that to continue to be good stewards of the land, we have to be sure that those antibiotics don't cause harm. The milk from sick cows that have been treated with antibiotics is a waste product on dairy farms. We obviously can't and don't sell it, but to just pour it down the drain would be irresponsible, to say nothing of expensive. Let me introduce you to one of my former graduate students, Heather Latier, and let her tell you about her research on this issue.
Thanks, Dr. Knowlton. I'm excited to talk with you today about my master's thesis project, which was antibiotic resistance gene abundance in the feces of calves fed perlomycin-dosed whole milk. The World Health Organization has deemed antibiotic resistance a natural, unstoppable phenomenon exacerbated by the abuse, overuse, and misuse of antimicrobials in the treatment of human illness and in animal husbandry, aquaculture, and agriculture. Antibiotic-resistant infections are responsible for over 2 million illnesses per year in the United States, resulting in over 23,000 deaths annually. The World Health Organization projects that by the year 2050, there will be 10 million deaths per year globally due to antibiotic-resistant infections. And that's a pretty scary number. Not only are scientists and public officials taking notice of antibiotic resistance, the public is also becoming increasingly aware of their contribution to antibiotic resistance. But not only are they becoming aware of their contribution, they're also becoming aware of animal agriculture's contribution to the issue. And therefore, as members of the dairy industry, we need to be aware of the role our industry plays in this growing problem. Before we explore further, here are some things you need to know about antibiotic resistance. Antibiotics are often dosed on a weight basis, so this data is a little bit skewed, but it still shows that the vast majority of antibiotic use comes from agriculture. Livestock operations are often considered reservoirs for antibiotic resistance. They're responsible for more than half of the antibiotic use in the U.S. In 2009, over 28.8 million pounds of antibiotics were sold and distributed for use in food animals. And about 90% of these antibiotics were used for disease prevention and growth promotion, rather than to treat an illness in animals. The use of antibiotics has been shown to lead to the selection of bacteria that are antibiotic resistant, due to the presence of antibiotic resistance genes. The World Health Organization has classified animal agriculture as one of the main human actions contributing to the acceleration of the emergence of antibiotic resistance. Antibiotics are used for three main reasons within the dairy industry. They're used therapeutically to treat diseases such as mastitis and pneumonia. They're used prophylactically to prevent disease, and this is most commonly seen in dry cow therapy. They're also used for growth promotion, which is low-dose, long-term administration of antibiotics. And most commonly, we see this in medicated milk replacer, which is fed on about 63% of U.S. dairy farms. However, due to increasing FDA regulations, this number may not be indicative of what is going on a dairy farm to date. And I think that likely more farms are feeding non-medicated milk replacer than they were previously. It's important to note that most antibiotics used as growth promoters, like bacitracin, are not commonly used in human medicine. But antibiotics used therapeutically, such as beta-lactams and glucosamides, are important for human health. But today I'm going to focus on a common source of antibiotic exposure in the dairy industry that hasn't received a lot of attention to date, and its potential effect on antibiotic resistance gene proliferation. And that's non-saleable milk, or waste milk. Non-saleable milk is a pretty self-explanatory term. It's any milk that can't be sold. And this can occur for a variety of reasons, including the presence of medications such as NSAIDs, a high somatic cell count, the presence of transition milk, or the contamination of antibiotic above the maximum residue limit, which is 100 microliters per kilogram for Pursue. Waste milk is fed on about 30% of U.S. dairy farms, but it's more commonly fed in the western U.S. than it is in the eastern U.S., and it's even more commonly fed in Europe. We chose Pursue for this study because it's commonly used for mastitis treatment, and it's extremely stable when heat treated. Additionally, it's known that more than 60% of Pursue administered intramammary is excreted into the milk, and so this is likely an antibiotic that calves are being exposed to when they're fed non-saleable milk. When feeding non-saleable milk, there is a set of advantages and disadvantages that go hand in hand with the practice. Some benefits of feeding non-saleable milk include a decrease in the cost of raising a heifer by $34 from birth to weaning. Additionally, when this milk is pasteurized, an increase in growth rate and a decrease in morbidity and mortality are observed. However, these benefits are not observed if this milk is not pasteurized. Some disadvantages to feeding non-saleable milk include an increase in labor and management because of the need to pasteurize and manage this milk. Additionally, there is less consistency in this diet when compared to milk replacer. It's important to note that the bacterial content of non-saleable milk is higher than milk replacer even after pasteurization. And if this milk is not pasteurized correctly or is not managed correctly or fed within a reasonable time frame, the bacterial load within the milk is much higher than milk replacer, especially if the bacterial content was initially high. And this increases the chance of exposing the calf to pathogens that they would not normally be exposed to. Additionally, the presence of antibiotic residue within the milk is something that must be considered, and pasteurization has been proven to be ineffective at decreasing antibiotic residue. There are some treatments such as pH adjustment, fermentation, and addition of antibiotic degrading enzymes that have been found to be effective at reducing antibiotic residue, but no treatment is able to completely remove this residue. And therefore, when calves are being fed non-saleable milk, they are being exposed to whole, functional antibiotic. So all of this information led me to my research question, which was, how does exposure to antibiotic in non-saleable milk affect the development and enrichment of antibiotic resistance genes within the dynamic calf gut? For this study, we fed 8 female Holstein calves pasteurized whole milk. Half of the calves received milk with a spike of Pursue in it that was indicative of what might be present in the milk of a cow receiving Pursue for mastitis treatment. The calves were bottle fed this pasteurized milk until 43 days of age, and they were also allowed unlimited access to non-medicated starter grain and water. Calves were initially fed twice daily, but at day 36, milk offered was reduced by half. All calves were weaned when 1.8 kilograms of grain were being consumed daily, and they had reached 43 days of age. All calves were able to achieve this. The calves were housed individually in hutches for the first 46 days of life and were then moved to group pens for the remainder of the study. We collected fecal samples weekly, beginning at day 1 of age and finishing at day 85 of age. DNA was extracted from these samples and was subjected to a quantitative PCR for antibiotic resistance genes. We analyzed for 16S rRNA gene copies, and this gene is an indicator of bacterial abundance. We use this to normalize our data. We also analyzed for TET-W and TET-O, and these are common genes coding for resistance to tetracyclines. We chose these genes because not only is tetracycline resistance extremely common, it's also relevant to both human and animal medicine. Finally, we looked at ERM-B, which is a lincosamide resistance gene, and we selected this gene because pursue is a lincosamide. Each of the 3 resistance genes were present in the vast majority of samples, including samples from control calves that had never been exposed to antibiotics, as well as samples collected at the initiation of the study. For example, TET-W was detected in all day 1 samples, and TET-O was detected in 75% of the day 1 samples. URM-B was detected in 87% of the day 1 samples. This shows that antibiotic resistance genes are present in feces from calves that have never been exposed to antibiotics. Similar results were observed by Tanz and colleagues and Sato and colleagues, Tanz using similar techniques to ours, and Sato using a primarily culture-based technique. Our results showed observed differences in absolute abundance, but not in relative abundance. And what this means is that the number of antibiotic resistance genes in the feces were higher in calves receiving antibiotic dose milk than those receiving milk without antibiotics. However, when these numbers were put on a proportion basis, so the number of antibiotic resistance genes for the total population of bacteria, those differences were no longer observed. And this leads us to consider the environmental effects of feeding this antibiotic versus the effect that it might have had on the calf gut. And these environmental effects are really important because it's known that the resistance gene levels are higher in water that's proximal to agriculture when compared to water that's not located near agriculture. So here we observe that the fecal shedding of TET-O and TET-W, the tetracycline resistance genes, were not different between treatment groups. But we did observe an increase in the fecal shedding of URM-B in calves receiving pursue in their milk. So this study opens the door for a lot of future work that can be performed because it shows that feeding practices can influence antibiotic resistance proliferation. We have some really exciting deep sequencing data to come that's going to tell us a lot about what's going on within the dynamics of the bacterial community in the feces of these calves, and it's going to give us a lot more information than we've provided here. This work has also led to some really interesting questions about what would happen or what does happen on farms where we're feeding antibiotic-containing milk, this waste milk, with many different antibiotics, not just one antibiotic like we looked at here. And I think that that's a really important study that needs to be done in the future. And it also leads us to maybe do some research looking at the way we treat our manure or manage some of the waste milk on our farms that maybe we're not feeding to calves, opening the door for a lot of research on management practices on the farm. Thanks for listening today. I hope you learned a little bit about antibiotic resistance and its proliferation and potential dissemination when feeding non-saleable milk.